ideally hear me?
Yes.
Okay, perfect. Good afternoon, everyone. Thank you all for still being here after 3 hours of lectures and tutorials. And I'd like first to thank the organizer for making this event. I think it's a very good idea and very good opportunity for us to actually share what we do outside of our very, very narrow surroundings and environment. And what I will try to do today is to introduce you in a very practical manner what really is a high-order mesh generation in the context of NEKTAR++ and specifically with our high-order mesh generator, NekMesh. Yeah, I'm a postdoc at King's, so please feel free to contact me whenever you have any problems with that. So why are we here? And when we're talking about meshes, usually we have this moment that everybody really wants to use meshes, everybody wants them to work, but nobody actually wants to work on generating the algorithms that generate these meshes. And this is even more true when we're talking about high-order methods. And it's very often that there are a lot of misunderstandings. So I wanted to actually show what is different in terms of high-order methods versus low-order methods. And to show that, I have took this paper that was recently published in Physics of Fluids, where a group generated a flow-around cylinder, Warshari simulation, very good resolution, and with finite volume solver. In fact, there were many people asking, mentioning OpenFOAM. This was done with OpenFOAM. The mesh around the body looked, as you can see here on the first figure. And then exactly the same group simulated exactly the same geometry, exactly the same problem with NEKTAR++. And their mesh was about 5 times larger in terms of size. So you can clearly see that the first conclusion that we can make is that the meshes, and it was mentioned many times earlier, the meshes that we use in higher-order methods and in NEKTAR++ are significantly higher, higher in terms of size and significantly coarser. And this is great. In this particular case, it was found that it was much cheaper than OpenFOAM. But if we go coarser and coarser and coarser, and we have a curved geometry, then we should start asking ourselves about the geometrical accuracy of the method. And it was mentioned earlier, but high-order methods are agreed to be very accurate and to have very low dissipation. But if you use a high-order method and you use a linear coarse mesh, you might actually end up in a very, very oscillatory solution. And this is, for example, a flow around NACA 0012, very coarse mesh. And what you can see that if you use a geometry of polynomial order 1, like finite volume mesh, what you have is a very oscillatory behavior. And what we usually do in our community, and it has been done for many, many years, you can do it in quadratic. Okay, quadratic mesh looks better, but if we zoom in on the leading edge again, you still have this oscillatory behavior. And that's why sometimes we go to even higher orders, P3, P4, and we actually start getting the pressure distribution on the body that we want. This was a particular example where I had to decrease a lot of the dissipation that we use, but this is just a demonstration that we can actually show with a good certainty that we use coarser mesh in the finite volume, but we need them to be still geometrically accurate, and because of that, we generate curved meshes. So what do we want to do in general with these pipelines and high-order methods? We start with some kind of a cut or your geometry. Then we generate a linear mesh with the desired resolution. In this case, it's coarser than the finite volume one. And in the end, we would like to curve it and elevate and put all the degrees of freedom that we would use in the solver in the NEKTAR++. And in the end, of course, we want them to be valid. We want to be with good geometrical accuracy. So what's the problem? Can't we just project everything on the boundary, on the cut, and go home, maybe simulate it, have our great, very accurate solution? And sometimes we can, but very often what happens is that higher-order methods, and particularly projection, like this, projection to the cut, end up taking the smile away of our face, and we create during the projection an invalid element, and the whole mesh becomes invalid. So what happens over here is that our mesh is self-intersecting, or this particular element is self-intersecting itself, which automatically many of the methods become unstable and they will generate, they will basically diverge if run at all. So this is the problem, and this is another demonstration. Here you have a quadrilateral layer that you would usually have with viscous type of problems. You would like to have very highly stretched elements. And yeah, again, if you project just the boundary on the cut, you tangle the element. So at this point, many people, if they try that, come to me and they say, oh no, I need to use curved meshes, but I cannot generate them. But we have worked in the past maybe 10, 15 years in the group. The group leaders, Dave Moxie, Joaquin Peiro, Spencer, as well, in generating a workflow or multiple workflows inside our mesh generator NekMesh that will actually alleviate these problems, and it will give you ways to generate geometries, to generate meshes around geometries of a very different type of complexity. And there are two main pipelines. The first one that I would like to focus shortly is what we call the academic workflow or the bottom-up approach, where you give us a cut, we generate the linear mesh with NekMesh, and then we use state-of-the-art high-order meshing tools to curve the mesh and to improve, optimize the surface mesh and optimize the volume mesh itself. What I would say for this workflow is that we recommend to use it for relatively simple geometry, so you can use it for any kind of 2D geometries, but when we go to 3D, I would recommend you to use it for simpler stuff like boxes, pipes, maybe something like, for example, a flow around an extruded wing is also something. But if you want to go to very, very complex geometry, which I will show later, we have an alternative approach, which is our industrial high-order meshing workflow. This is a very recent development where we outsource the complexity of generating a good linear mesh, even maybe with the boundary layer. We outsource it outside, so you use your own favorite tool that you have used maybe in OpenFlow, maybe you have used in StarCCM, maybe you have used it in Fluent. You generate your mesh there, you know how to do it. We don't ask you to learn a new tool. You generate your linear mesh, you give it to us, you give us a cut file, and from there on, it's up to us to actually generate the high-order mesh. At least that's the idea behind it. Okay, let's start with the first workflow. This is the bottom-up approach. The files that you need to provide to us are cut, usually in a form or a step file, even though we usually support also geofile to some degree. For the people that use Gmesh, this will be familiar. And we also support, we also require you to provide us a file which contains all the settings for your mesh generation. I'll go into the details a little bit more in the next slide. But what would I want to point out here in terms of our cut file is that this cut file needs to be topologically valid. This means that it should be watertight, so you shouldn't have gaps around the body. The normals needs to be pointing out inside the domain, and also you cannot have intersections of cut surfaces or something like this. So that's why we usually refer it as academic, or if you have simpler geometries that you know that your CAD is perfect, then I would recommend you using this one. And finally, something that it's important is that you would like to have also the topological layer of your mesh. So this would mean in 2D, it's not sufficient to just have this drawing here, for example, in CATIA or in other CAD tool. It's not sufficient just to have the drawing, but you need to actually, after you create the drawing, you need to fill it with a surface in 2D or with a solid or volume in 3D. Okay, how about the mesh settings? The mesh settings in our case are coming into an XML format in a file that we put NCF extension, and it looks the following way. So first of all, we give some settings for the linear mesh generation. So this would be, of course, your step file. Usually would like to have it in the same folder as your mesh that you will be running, or your case where you will be running. Then the mesh type. The 4 different mesh types that we support for the linear mesh generations are 2D, which will generate your triangular mesh, 3D tetrahedra, a 2D boundary layer and 3D boundary layer. So what this will do is will create a thick single quadrilateral or prismatic layer around the body of the surfaces that you select, and inside the domain you still have your triangular or tetrahedral mesh. Of course, you need to select the settings, so minimum and maximum size. And we also have curvature refinement, which is a function of this epsilon, and the epsilon is multiplied by, sorry, not the epsilon, but the square root of epsilon 2 minus epsilon is multiplied by the radius of your curvature, which is 1 over the curvature, if someone is interested in more details. And that's how you can calculate your size in this particular area and increase the size in this particular area. In terms of higher order information, the only thing that we require from you is just to tell us with what polynomial you would like to approximate the geometry. So what polynomial will be used to interpolate the geometry? As it was mentioned earlier, we use isoparametric elements, which means that we use exactly the same polynomials for the solution, but also represent the geometry. And we have also the boundary layer. So whenever you select the 2D boundary layer or the 3D boundary layer, we will create, we need to select what surfaces you would like to have these boundary layers, boundary layer meshes, what is the overall thickness, number of prism layers that you would like to have, and the progression ratio, where the progression ratio is, if you have an element on the bottom, which is h, you have r times h. And the values usually we would go for this is between 1.3 and 1.8 for most of the industrial cases that I have been involved with. And finally, we can actually generate also a refinement zone. How do we generate this refinement zone? We literally create a line, so 0.1, 0.2, and the coordinates of this line. We have a radius out of it as a domain of dependence. And finally, of course, we have our desired mesh size in this particular region. This would generate the mesh. It will use a surface mesh optimizer, but in the end, we also actually have a volume optimizer, which can improve our mesh quality, and it can solve the issue that I showed earlier and put the smile again on our faces. And this is the volume optimizer, or how we call it, variational optimizer internally. I must point out that this volume optimizer is memory heavy. So if you use it, please make sure that you have enough memory. This would be very heavy, like this would be probably a high memory machine, let's say 64, 128 gigs of RAM. If you want to use, this is optional. You don't, in most cases, if you follow the step that I will say later on, you don't really need to use it in most cases. So how do we run it? How do you run this academic pipeline? It's very, very simple. You just say NekMesh, your setting file, and then you want to have your output file, let's say mesh.xml. Very often, people generate 2D meshes, and they want to extrude them in the Z direction, so the 2D mesh in XY, and the third direction is Z. So you can do that again with this pipeline, and you can call the following module, which is NekMesh, your input mesh, the 2D mesh that was generated in this case, the output mesh, and then you can use the module or process modules, how we call it, extrude, and you can specify how many layers you would like to have in the Z direction and the length of this extrusion. We'll have a tutorial later on. It's a NekMesh 01 cylinder. I think people that are using Linux and Windows will be able to run this. For the RM people, they will have to probably build from home later on. Okay, but what is actually unique about NekMesh and the way we are producing it, and more or less also where we are focusing on more and more from the geometrical perspective, is how do we go to industrialization? How do we go to very, very high complexity in terms of meshes and geometries? And this is what I've been working recently, and what we have released is the industrial mesh generation workflow, where the linear mesh, we leave it to you. We know that you know how to generate your meshes. We know that you know how to generate your prism layers around the body. Okay, let's do it the way you have done it all the time. We have done CFD before probably, and then let's take everything on our side afterwards. And to do that, we introduce a new module, which reconstructs the connectivity between the mesh and the cut. So let's start step by step. So what kind of meshes can we actually read? So we can read many different formats. So in terms of all these tools that you see here, so we can read star CCM, Gmesh formats in both a linear and a high order, linear pointwise meshes through the Gmesh format, and very recently we have started also reading ANSA meshes also with, we have a new input module, which is the CGNS one. If you do not see your favorite formats in this list, I recommend you have a look at the Python library mesh.io, because it's very likely that this format that you use can be converted to Gmesh through mesh.io. So how would the linear mesh look like? The linear mesh that we recommend you to generate is, as I said, coarser than your finite volume mesh. But what is important here and what will make your life easier, though it's not required, is to have a thick layer around your body that will allow you to actually get the curving process automatically. So it will not tangle, it will not self-intersect once you curve your mesh. This is an example. Here we have blue prism layer, O-type prism layer that goes around the full NACA 0012, and as the core mesh, we have a tetrahedral. The type of meshes that we support, otherwise, it's pretty much everything that you can think of in terms of common finite element mesh types. So like tetrahedral, prismatic, pyramids, and hexes also as well from recently for this workflow. Okay, you have your linear volume mesh. You have generated it in your favorite tool. So let's go to how do we curve it? Oh, more precisely, what kind of cut can we use here? And this is one of very, very strong point of our workflow, is that you can separate the cut file or the geometry file that you use for your linear mesh generation in your third-party tool from what you use in NekMesh for the high-order part of it, or for the mesh curving and the mesh optimization processes. So here is an example where you can have only a part of your body. So this is just the curved part of the NACA 0012, which is just a single nerve surface that we have provided without the domain, without any other parts of it. And you can do it even with part of your cut if you have a very, very complex domain. So we have our cut, we have our linear volume mesh. The next step is to reconstruct the connectivity between the linear mesh and the cut, because we support the process where these two are not connected at all. So you can have a mesh that you have generated 5 years ago somewhere in a folder that you have forgotten, and you want to rerun the case with NEKTAR++, no problem. Let's take this mesh. You can generate somehow a cut, or you can find the cut somewhere in your files. You give us these two, and it's very likely that we'll be able to generate the high-order curved mesh out of it ourselves. Important, we try to have as little assumptions as possible for the linear mesh. And I would say the only assumptions that we would like to have is that the vertices of the linear mesh, so this would be these points over here, are relatively close to the cut. And what relatively close to the cut means, we will talk about the tutorials, but again, if you have something that it's cut that is 3 meters away from, sorry, if you have a linear mesh that is 3 meters away from the cut, then yes, of course, we will have problems with it. Okay, so we have this connectivity. The next part is to actually curve the mesh and run our optimization modules. So in terms of mesh curving, we project the edges and the faces on the cut, on the surface mesh. What happens is that very often you have extremely distorted surface elements, and we use a surface mesh optimization, and then in the end, we use a volume mesh optimization with, as I said, with the variation optimizer. This is optional again. Okay, an example, very, very coarse example to see how far we can go. This is just for a visualization. Please don't expect to run that coarse meshes. And this is like with the curving, we can actually have a good geometrical accuracy even with the 4 elements. And if you want to go, for example, to slightly finer mesh, same spherical mesh, you can see the mesh quality. The mesh quality in high order meshes, usually we calculate with scaled Jacobian, which literally means how distorted your mesh is from the linear mesh. And if you use all the optimizers, you end up with something that is much closer to the ideal value of 1. So just to be aware, if you have any elements that are with negative Jacobians, this means negative volume. This means that any kind of high order method or even low order methods will have problems with that, and you cannot run. So this is the problem that we introduced in the beginning. So Jacobian of 0 is the minimum that you can have, and we don't recommend it. The closer to 1 it is, the better. Okay, let's just show several examples. So what I meant by industrial geometries, very often we go to something similar. So this is one of the cases that we have run many, many times, the imperial front wing. This is coming from Formula One geometry from 2003 or 2004, but it's very good to actually show what we are talking about. So you generate this coarse linear volume mesh, again, prism layer, O-type prism layer, tetrahedral elements. We curve the mesh, and you end up having a surface mesh that looks as smooth as this photo. So this is not the geometry itself. This is actually the surface mesh. And if you want to see the comparison between the linear mesh and the high order mesh, you can also see the high order nodes that you would use on the surface. Of course, this still is a volume mesh. I'm just showing the surface mesh here. And please, of course, you will need to have much finer meshes than what I'm showing here. This is just for the demonstration to see that you can go to a higher polynomial orders and you can have like good geometrical accuracy with very coarse meshes. Usually, we would recommend doing P3, P4 polynomial order. Okay, we have our high order curved valid with good mesh quality mesh. So many of the elements look like this. So we have prisms around the body. So the green part here is a prismatic layer. So we have the prism that it's curved, and we would like to actually propagate the curvature inside so we can generate a good Y plus resolution. So for the people that come from the CFD world, this is a very common scenario for us. NEKTAR++ is very well optimized for incompressible and compressible Navier-Stokes, as Guillermo mentioned. And many of our applications are related to that. And in pretty much all of these cases, you're interested in resolving the boundary layers around the body. So you would like to have something that looks like this. But in order to do that, we take these coarse elements and we split them. For the people in finite elements, we split them in the reference element. So this would be your reference element. And by doing that, we actually keep the validity, keep the geometrical accuracy, and we can also do it much faster in terms of computationally compared to if we actually optimize the full mesh with all the different prism layers. Okay, just an example to let you know what kind of geometries we have meshed. Many of them run. Yeah, I mentioned that we're heavily working in motorsport. So for example, Imperial Front Wing, there's several others that have been meshed as well. But also we have also applied that to turbo machinery cases. Guillermo has run many of them with NekMesh. And recently we have actually done also the full high lift prediction workshop, the most recent high lift prediction workshop where you have a full aircraft with extended flaps, with extended slats. And yeah, there you have some other problems that we are currently, hopefully soon, introducing to the master. So basically we introduce their solutions to the master. And finally, how do you actually do all this? We will use the NekMesh module system where you just say NekMesh module and what you want to do. And this is how it looks like. So first of all, obviously, we convert your third-party mesh to our XML format, which Victor introduced in our mesh. Again, you don't write your XML, linear mesh XML yourself. You just convert it, or you just generate it with NekMesh. And then we project or we curve the mesh with the following command. It's called project cut. Here, every single module that you would like to run in NekMesh, we put the argument -m. We run the volume optimizer, optional, as I said, with the following settings. Usually, I will recommend using the linear elastic one for 3D problems. We ensure mesh validity, so sometimes you end up that even your volume optimizer is not really capable of fixing all the elements, and you have 1 or 12 negative Jacobian elements. This means invalid self-intersected elements. In this case, if you think that this is not an important region, you can just linearize it. And this is the command that you need to pass just to linearize only these particular invalid elements. If you do something simple, you don't really need to think about that, but it's a good practice just to make sure that you have a valid mesh that you can run. And once you have this, it's exactly what I said with the boundary layer splitting or the isoparametric prism layer splitting, is that you basically select the surfaces where you have prism layers, progression ratio, number of layers. Depending on the application, you can go from 2-3 layers to 12 in some turbomachinery cases. And you need to select here. So initially in the projection, we selected an order, but after that, in many of the modules, this parameter NQ appears, which is literally just how many points would I like to have on an edge. It's, or in general, which is just polynomial order +1. So this would be your order that you selected here +1. And for visualization, we use heavily ParaView. Our post-processing tool Field Convert can convert the meshes to VTU and VTK. What you will see in the tutorials is just our legacy module. But if you build from source, and you do build with VTK, and you have also your ParaView maybe on your computer, you can use, and I recommend using this VTU high order, where you can use, first of all, it's going to be a significantly cheaper in terms of storage that it takes, and also it would actually show you the real isoparametric surface and not just a linear surface. And yes, in the end, what you would like to do is, this was just showing you the modules, but you don't need to input and output all the time. This is just for demonstration to see the different modules. In reality, you can run multiple modules sequentially, one after another. So as you can see, module 1, module 2, and so on. So for example, you can do mProjectCat, mVaropti, mLinearize, and so on and so on. And yes, I heavily recommend everyone that wants to do any kind of more complex geometry to do the tutorial on the afternoon. And this will work on all virtual machines that we'll be doing. It's the NekMesh 03 industrial pipeline intermeshing folder of the tutorials. We are heavily working on NekMesh. There are several PhDs, and I'm working as a postdoc as well on it. And in the past several years, we have actually introduced high order edge adaptation. We have to merge it with master soon. So there in the next several months, we will also give you the possibility to use edge adaptation, high order curved edge adaptation. You will do, so no need to remeshing. We'll do some we already did. We just have to merge it. Is some automation that will actually allow you to do most of it inside NekMesh and not go back to your linear mesh generator if something is very, very complex, like in this case. And yes, we are heavily working also in some optimization and adaptive mesh refinement, especially around the prism layers and the boundary layers of your mesh, both a posteriori and a priori. So before you run the simulation and after you run the simulation. And yeah, we have also generated some HP, HR, and HRP refinements that hopefully in the next, this probably is more of a midterm of what is coming probably in a year or year and a half for the HP adaptation. And yes, with that, I'd like to thank you for your attention. If you have a whole workflow that you would like to do a lot of geometry, so many people do machine learning, many people do industrial geometries where they have their own pipelines in industry, please feel free to contact us. There are a lot of things that we can help with, and we have already done a lot of that. So I think we are open. If you have my email, of course, you have the emails of some of the other group leaders. So we are happy to help. We're happy to help you. And yeah, with that, I would like to say just use NekMesh. And yeah, I hope you have a great afternoon and try to do the tutorials. I think they were going to show you what steps you need to follow.